Goes to presentation mode, I guess. Change the gears here and talk a little bit about the orbital sector, which is by all means part of the complexity in the realm of quantum materials. So I would first like to acknowledge, of course, our funding sources, which is DOE, and various facilities that we have used to carry out our experimental work. The stuff that I'm going to show here is has been actually a part of it published in this communication paper. Next, I would also like to acknowledge that this is a work of pretty broad collaboration. Various people have contributed to various aspects of this work. I'm not going to name them all. I'm going to just say that samples that we have used come from the group of John Mitchell at Argonne and also Chedimir Petrovic, who is our local guy at Brookhaven. Fine. So, in the complex materials arena, a lot of attention has been paid to the low temperature physics, where basically all the colorful action takes place. However, not as much attention has been paid to the high temperature regime. And so our interest, among others, is to look into the hidden local broken symmetry states away from the ordered phases. And in this specific case, we're interested in transition metal systems that have active orbital degrees of freedom with partial filling of the d orbital sector. And in those systems, in principle, in high temperature, you deal with high crystallographic symmetry, which imposes orbital degeneracies. When you look at the systems from the average crystallographic point of view. And so the question that we are asking really is what happens locally at high temperature. And to that effect, we employ local structural technique, which is X-ray pair distribution function. That does not actually take presumption of periodicity and provides information on atomic structure on different length scales. Okay, so to set the stage, I would like to refer to a childhood friend, and the definition of a childhood friend is actually dual. One is it's the person that basically is always there for you to provide you help, and the other is a little bit more negative. It's the person that you cannot get rid of no matter what. And so in that context, I'm going to refer to, I will give a little introduction to orbital degeneracy lifting in retrospective of perovskite manganites. The basic building blocks, and I'm sure all of you or most of you actually know about these systems or have actually studied them. The basic building blocks in perovskite manganites are manganese oxygen octahedra. And manganese comes in different charge flavors. If manganese ion is free, it has 3D sector completely degenerate. If you put it in octahedral crystal field, it splits into EG and T2G manifolds. And then depending on filling and other interactions that I'm actually not going to mention, the orbital degeneracy is being lifted through so-called Jahn-Teller effect, which actually involves lattice distortion. Now, this lattice distortion is pretty strong, and of course, since it's a lattice distortion, you can sense it in the structure. And so this is a materialization of 3+ and 4+ manganese states in 113 manganites, calcium and lanthanum versions. And you can see that when actually manganese is 3+, meaning when it has 4 electrons in D manifold, you do have a distortion. This is a neutron PDF. And when you remove that electron, that's a calcium variant, basically the distortion goes away. Fine. So another aspect is that the lanthanum version of the material exhibits a well-known long-range orbital ordering transition at around 700 Kelvin, which is basically known as Jahn-Teller transition. And so it goes into Jahn-Teller phase of cooperative Jahn-Teller distortion. According to crystallographic assessment, this distortion, as you pass into the high temperature regime, virtually goes away, and then it completely actually goes away. It's crystallographically prohibited all the way up in the crystallographic rhombohedral regime. Now, This is actually the bad part of the old friend, and this particular picture is not quite right. It led to a perception, at least in part of the community, that the orbital degeneracy is being lifted at the long-range structural transitions that are symmetry breaking. Another thing that I want to point out in passing is that the energy scale of the orbital degeneracy lifting is of the order of electron volts, whereas the transition corresponds to energies that are of orders of magnitude smaller. Okay, so if you take a local view, you immediately see that basically this transition is of order disorder type, and that the distortion locally persists. You can measure it, and you can basically see that the distortion that is responsible for lifting this degeneracy does not really care about the transition. So I'm going to call this high temperature phase for the purpose of this talk, and in principle, orbital degeneracy lifted phase. And the state in which we are there, we are actually in orbital degeneracy lifted state. Notably, in this particular case, it is continuously connected with the low temperature cooperative regime. Now, at this point, I'm going to change the gears, and I'm going to go into a different corner of the materials universe that displays exotic orbitally ordered phases. And I'm going to basically pass through, I'm going to do a little walk through materials world that display orbital molecules. I'm going to start with simple ones, basically a spin singlet on a dimer in a famous vanadium dioxide. So this spin singlets, the signature of this spin singlet state is a drop of magnetic signal in magnetic measurements at the transition, and the formation of a very short metallic bond that corresponds to this spin singlet dimer. And in this particular case, there is of course high temperature metallic to low temperature insulating transition. Now, this is not an isolated case. We can basically see that it happens also in Magnelli phases, like so. Interestingly enough, all that work has been done initially like 60+ years ago, just like manganites. Or niobium dioxide. Again, we have a sharp drop in susceptibility. Here is a more recent work where basically we see a sort of cartoon of partial charge density of occupied d orbitals as it comes from the FT calculations. So at low temperature, you have dimerization that presumably looks like so. And at high temperature, you have no dimers, and this is its depiction. Now, it's not all dimers. These objects can actually take complex topologies. So here is an example of various systems that display octamers or helices or heptamers, all of which more or less actually have the same sort of response in the magnetic signal. It also spans materials with different lattice topologies, such as, for example, this honeycomb in the routinate system, or famous magnetite that basically exhibits these trimerons. So that being said, with all that complexity, I'm going to actually focus on two related spinels that exhibit orbital selective pulse transition. This is copper radium 2 sulfur 4, which exhibits octamers, and the titanium version, magnesium titanium 2 oxygen 4, that displays helices. I'm not going to be concerned with specific topology of the low temperature phase as such. Both systems exhibit metal insular transitions. They are Pauli paramagnetic at high temperature and non-magnetic at low temperature, and the symmetry changes from high to low across the transition. And it's basically assigned, this behavior is assigned to orbitally driven MIT. Good. So, as I said, they have cubic spinel structure, which has this block form. And underneath, there is a pyrochlore sublattice of corner-shaped tetrahedra of transition metals, whose d orbitals happen to actually overlap along the edges of this regular at high temperature cubic sublattice. As you go to the low temperature regime, you get all this complexity. So in iridium case, it's, as I said, octamers. In the case of titanium, you essentially have these helices. And the corresponding phase diagrams look like so. They are very similar. There is a drop in susceptibility, jump in resistivity. And what I will review here is actually stuff that is relevant for the talk. So in the iridium case, valence is 3.5 plus. That appears to be actually non-trivial, and it originates from actually 1 plus valence state of copper. The filling is D5 plus 5. I'm sorry, 5.5. The system exhibits at low temperature charge ordering, orbital ordering, and spin singlet dimerization. And non-trivially, it has actually 1 hole per iridium T2G state, which is in high temperature cubic regime, triply degenerate. On the other hand, titanium is always in valence 3 plus, and it has filling of D1. There is no charge ordering, as opposed to iridium case, where actually there is charge disproportionation taking place at the transition into 4 plus and 3 plus species. There is orbital order, spin singlet dimerization, and as I said, there is 1 electron per triply degenerate titanium T2G. Okay, so in what follows, I will actually show you that the high temperature regime can be regarded as orbital degeneracy lifted regime with orbital degeneracy lifted state, and in some sense similar to what I have shown in manganites. However, this state is discontinuously connected to the ground state. Okay, so first we will actually review indicators of orbital degeneracy lifted state, assuming that it's there, and we're going to do most of the stuff for iridium version, and then I'm going to briefly actually review what happens in titanium. For that purpose, it's useful to compare sulfur and selenium version of this iridium spinel. Those sister compounds are isostructural and isoelectronic, yet one displays metal insulated transition, the other doesn't. One is actually a very good metal, selenium variant. The other is not. The other is actually having resistivity that is not really metallic. It's actually orders of magnitude or order of magnitude larger than it should be to be considered a proper metal. And it has various other anomalies at high temperature, such as weak Fermi edges and glassy thermal conductivity. So one of the questions that we wanted to understand is, or to answer, is why this high temperature regime has such poor metallicity in the sulfur case. And one natural thing that you can actually inherit from sort of manganite logic is that maybe, just maybe, those dimers survive in the high temperature phase. That has been actually implicated theoretically. And so the signature of dimers in structure is that it has this short metallic bond. So this is iridium-iridium bond that is non-dimerized, and then fraction of iridium dimerizes at low temperature, and it creates this small peak. Well, then it should be relatively simple in PDF to basically explore if the dimers survive in the high temperature phase by simply plotting the waterfall plot of all the data spanning a broad temperature regime from low temperature to high temperature. And as you can see here, this little peak, which is actually a dimer peak, clearly disappears in the metallic regime. So to our disappointment, the answer was that the dimers disappear even locally at high temperature. For what follows, I'm going to actually show you here at the bottom a calculation of basically the decomposition of total X-ray PDF of this system into iridium-iridium pairs, shown here in green, and its complement shown in red. And so what you see is that this very tall peak is actually nearest neighbor iridium-iridium peak, and that there is very little or actually almost none of any other contributions. So by looking at this peak, that's the peak that I'm talking about, we're essentially looking at the structural signature of direct structural signature of T2G orbital overlaps in this system, because nearest neighbors are on the pyrochlore sublattice of, in this case, iridium, and T2Gs actually run along those edges. Fine. So what we have done next is we went deep into the high temperature regime and fitted nominal cubic model to to this data. And what you observe is that the fit is spectacular all the way. So except underneath this peak that corresponds to iridium, which sort of shows this very delicate signature. This signature survives to the highest temperature measured. In this case, it's around 800 Kelvin. We could not go higher because the system presumably decomposes. If you interrogate the difference curve as a function of temperature, you can estimate the correlation length of this effect, and you can basically see that the correlation is pretty much temperature independent, and it grows dramatically exponentially sort of as you approach the metal insulator transition from above. So we have, if this is a real effect, basically discovered something that relates to the pairs of iridiums that is actually not long range ordered. And we can understand that because basically iridium, each iridium has 6 neighbors, and it has 3 different directions in which this state, whatever it is, can be formed. And thereby it can actually, through special temporal fluctuations, average to cubic. Fine. But that was not enough. Of course, we wanted to prove to ourselves at first place that this is an electronic effect. And so we embarked onto a series of studies using judicious substitutions. So first thing that we did was we actually doped zinc on copper site. Zinc in tetrahedral environment solely comes as 2+ and represents basically electronic doping. And so as you dope electrons, what you see is that this peak, which is solely or 95+% coming from iridium-iridium pairs, dramatically responds. And it responds in such a way that when you go from 0% zinc, which is actually blue, to 70% zinc, which is red, it actually, this distribution becomes narrower and sharper, which is to say that whatever distortion there was, it actually gets removed, which serves as a beautiful example of actually structural evidence of electronic doping, actually electronic transfer from zinc to iridium. And it also serves as proof that what we see is indeed electronically driven. Another aspect of it is that when you actually measure the Debye-Waller factor of iridium site as a function of zinc content at room temperature, you see that it actually drops dramatically, which suggests that whatever distortion there was, which is uncorrelated structurally, gets removed from the system. Fine. So we have also done cubic model assessments of our data. So here is our effect in the original sulfur system. And we see that as we dope sufficient amount of zinc, meaning as we change filling from 5.5 towards 6, we're removing the effect in zinc substituted system. On the other hand, if you put chromium on iridium site, and chromium is appreciably smaller, and it actually contracts the lattice, what you do see is you see enhancement of this effect. So pressure presumably stabilizes this effect. So in principle, you have knobs to manipulate this state pretty nicely. Now, what happens to our other sister compound, selenium? What happens is that this actually is cubic at all temperatures, and it's cubic at room temperature as well, and does not display this state. Basically, this state is missing. So cubic model explains local structure perfectly well. If you pay a close attention, you basically see that this iridium-iridium peak in selenium variant is actually at a higher distance than in the sulfur variant, meaning that basically the pyrochlore sublattice is expanded, and therefore the orbital overlap is actually reduced. Fine. So we have assessed or quantified the distortion associated with this state by fitting a tetragonal model. I don't have time to go into those details, but I'm just going to say that that this is the distortion assessed through this modeling as a function of nominal cubic iridium-iridium distance. And what you can see is that you can actually drive this distortion up and down and basically get rid of it completely as you dope electrons, in this case by substituting zinc, or you can actually pressurize it and increase it. And then our sister compound copper iridium to selenium 4 actually is placed on this diagram right here, which gives us an idea that maybe, just maybe, if you apply pressure and you bring basically the interatomic spacing between the iridiums back to this line, you will invoke metal insulated transition. Interestingly enough, this hypothesis has been actually tested 30 years ago, and people just did not know what it means in this context. And that is that actually pressure, it indeed induces metal insulated transition in selenium variant. So presumably the application of pressure to this system basically induces MIT by enhancing T2G orbital overlap and thus enabling the ODL precursor state. In other words, you can label selenium sister compound as a latent ODL system, and it only really actually zings once you apply pressure and you allow for sufficient orbital overlap. Okay, so this has been a set of measurements on powder, so it's always good to test if the same type of phenomenon takes place in single crystals. And for that matter, we actually also wanted to address spatial character, 3D spatial character of this ODL state. And so for that purpose, we have actually performed so-called 3D differential PDF type of measurements, where basically you collect full map of scattering in reciprocal space, then you separate diffuse and Bragg, which is essentially critical for this. Bragg is your signature of the average structure, and diffuse is obviously measuring the deviations from it. And then you 3D Fourier transform it, and what you end up with is essentially a 3D map of interatomic vectors in space, which you can then interrogate in a model-independent way. And what we have observed is that the largest differences in the differential occur exactly at the iridium interatomic correlations. More interestingly, if you take a look at the diffuse scattering signal from specific directions, in this particular case, it's from the top of 111 axis, you see this highly structured diffuse scattering, which is, for those who followed this type of research, actually reminiscent of a signal that you get in spin and water ice. So the question is whether this is evidence of ODL ice at high temperature. The measurement was actually in the high temperature metallic regime. The other aspect of it is that when we look at specifically iridium interatomic vectors and correlations, we do reproduce that there is actually a distribution of iridium interatomic distances away from the average that is shown in this plot as green dots, and that pretty quickly fades out as you go to the second, third, and fourth iridium neighbor. Okay, so the correlation is actually very short. So this was quite satisfactory. Now I'm going to give you a little overview of the mechanism in what we think this means. So at high temperature in the metallic regime, basically you have iridiums that are actually having half a hole each in triply degenerate T2G manifold, and it's beneficial for the system to actually, for pairs of iridiums to invest one of its orbitals to create a molecular orbital type state to share a hole. And so there is basically only one orbital of each iridium that is involved, and it can actually form this state in different directions. Presumably, so I'm kind of showing this in this figure. So presumably that's the cartoon of the ODL state. It has actually one hole in the anti-bonding sector and 3 electrons. And as a result of that, actually 2 iridiums get closer together. Interestingly enough, because this is highly randomized, as I said, each titanium has 6 neighbors to make this state with. Basically, through special temporal fluctuations, this averages out to cubic what is observed crystallographically. Another interesting aspect is if you take one orbital state per tetrahedron, you can actually exactly map it onto the ice rules. This is not a proof, this is just sort of a conceptual cartoon. Now, as far as dimerization and metal insulated transition goes, dimers, spin singlet dimers are born out of transfer of charge from pairs of ODL states. And so in that context, it's a whole dimer. So if we have two ODL states like so, and if one of those electrons decides to jump onto the other ODL state, then this ODL, what remains is actually a dimer. On the other hand, the other ODL state that receives an electron will become actually D6, and in that sense, ODL inactive. So basically, the transition necessarily involves in this picture the transition of charge, a charge disproportionation, and so this process would then be responsible for generating 3+ and 4+ species, which are behind the charge ordering, and then ultimately orbital order triggers metal insulated transition. Okay, so that would be the scenario in this picture. We're going to move on to the titanium variant, which again, if you take a look at the resistivity, has a quite poor metallic state. And as it turns out, at low temperature, the system is in has tetragonal average structure, and at high temperature, it's cubic. And so if you fit the tetragonal model to the low temperature data below the transition, you get a much better fit than if you try a wrong cubic model. And so you sort of see in PDF over the first few peaks, you sort of see how basically the cubic model misfits the low temperature dimerized data that correspond to dimerized state. Interestingly enough, as you go to the high temperature regime, the tetragonal model again does a much better job than cubic model. Cubic model gives you a difference curve that is very similar to the one observed when you actually make a mistake on purpose. And so here, basically this is a summary of fit agreement factor, let's say, as a function of temperature for cubic and tetragonal models applied over 1 nanometer scale. And you see the tetragonal model does a better job at all temperatures. Okay, so it's always best not to rely on any models. So let's just take a look at the stack of data and see what happens as you actually cross the transition. So what you see here is a stack of PDF data doing exactly that. And what you see is that there is a signal that is associated with the dimer distance in this titanium spinel that actually disappears. It goes from blue, where there is some kind of distortion, to red, where presumably the distortion is removed in a pretty much continuous way. And that intensity is actually being placed at a slightly higher location. However, this peak does not show a standard thermal behavior. Standard thermal behavior would be as you heat up the system, basically the peaks become broader, which is sort of what this peak shows. It's a dominant effect on that peak. You can interrogate this difference curve, you can actually integrate it, and what you see is that there is a gradual decrease in the integrated intensity in this feature until it actually abruptly drops at the transition, and then it continues. In this particular case, 500 Kelvin temperature set was used as a reference to generate the differences between all the other data sets and then generate this curve. But the ultimate idea of what is going on in this system still comes from modeling. So we have fitted this tetragonal model as a function of temperature throughout the metal insulated transition. And what we actually observe is that there is, at low temperature, a dramatic distortion of titanium nearest neighbors, if you will, that is a signature of spin singlet dimer that gets removed at the transition, but it gets actually, it evolves into a much smaller distortion. However, it's not cubic, meaning it's not undistorted, which would be basically the case if all the data collapsed into this dashed line, suggesting that very similar set of events takes place like in iridium spinel. We have assessed the correlation length in this case through boxcar fitting. I'm not going to go into details. I'm just going to say that the correlation length of this local disorder is larger than in iridium case. It's of the order of 1 nanometer, and it appears to be temperature independent in this regime from 300 to 500 Kelvin. The distortion, by the way, persists to the highest measured temperature, just in the, like in previous case. We have not assessed this closer to the transition. This is sort of work in progress. Okay, so what is happening? Well, in analogy with the iridium system, we have a dimerized system here at low temperature. So those are this is just basically pyrochlore subatoms of titanium. These are dimerized titanium atoms, and presumably they carry charge of 2 electrons, and then there is basically different bond charge in between. So the dimer is described like so. In this particular case, we only have 1 electron per titanium, rather than half a hole per iridium in previous case. And in the high temperature cubic regime, we would have a distribution like shown in this middle panel. However, we know that that's not the case because that's not compliant with the structural distortions that you observe. So following the analogy with iridium, we would say, well, okay, if we have a dimer, to get rid of it, we actually have to get rid of one of the electrons. And so if you remove the electron, you end up with this one orbital degeneracy lifted state that corresponds to to shorter iridium, tellurium, no, titanium, okay, I got confused. Titanium contacts that are actually longer than in the case of dimers, but are definitely not as long as in the degenerate or non-bonding case. Now there is a problem, of course, and the problem is that the question is what happens with this other electron, and that leads us to actually a concept of 2 orbital degeneracy lifted state. And this is sort of a superposition of 2 one orbital degeneracy lifted states that are actually introduced with respect to, let's say, this titanium number 2. So if you have a dimer and 1 electron leaves in this kind of localized picture, it actually leaves into another orbital or another ODL state that is actually made from the orbital of titanium labeled 2 and neighbor labeled 3, but it leaves behind a single orbital degeneracy lifted state that 2 makes with 1. So in some sense, you have this state like so, and that is consistent. I have run out of time, or I can actually not hear you, but
yeah, you need to wrap it up.
okay, and so basically that is consistent with the observed distortion. That is his spatial extent that is longer. Okay, so to wrap it up, arguably these systems are very exotic, and in principle one could argue that this is fine, but who cares? However, just want to point out, this is my last slide, that similar behavior has been actually observed also in iron-based superconductors, specifically in iron selenide. In iron selenide, we know that there is a nematic transition at 90 Kelvin, in which basically, presumably, the degeneracy between X, Z, and YZ the orbitals of iron, takes place. An ODL type response has been seen in multiple actually studies, which I actually show here. And this response presumably persists all the way up to 500 Kelvin. So is this a nematic precursor to basically the nematic regime? And with that, I will actually wrap up. So this is my summary. Orbital degeneracy lifted state is discovered in iridium and titanium spinels displaying metal insulated transition. Presumably this state has a local character as actually as shown, and it's a high temperature precursor to what happens at low temperature. In the 2 spinels studied, this state enables the metal insulated transition and the richness of the observed ground states. The details of filling, geometry, and overlap are important for this state. And this ODL state might actually be quite common in transition metal systems. And so let me just close my talk by saying that the governor in quantum complex matter, sometimes the governor of what takes place at low temperature might actually be sitting at some place warm. And with that, I wish to thank you for your attention. I would be happy to take any questions.